So I assume that now you sort of are comfortable with, we know what's going to happen. We know that UV will start from the center of the sun, they will go to resonance. There is some value of PF. The value of PF will depend on data and square and theta. And it will depend on the density profile, how fast density. Then they will come to the earth. During daytime, it's very straightforward. At night, they will pass through the earth. Therefore, there will be some oscillations, and you will get some P1E and P2E, which are different from cosine square and sine square. That's what. So now let's go back to whatever we saw 2 lectures ago, what the sonar data shows us, and then we will see how we can explain it. So I'll first remind you of the solar data that we saw earlier again. Then we can identify the right solution. We will see that qualitatively the problem can be solved in many different ways, using many different solutions. We will see how to zoom in on the right solution. And then we will see how this solution was confirmed by using experiments at the experiments where you produce some neutrino flux and you get the most. So let's look at the solar data. Right. So we had this flux of neutrinos as a function of energy. EP neutrinos, beryllium, EB, boron, and so on. Cadmium experiments went from about 0.2 MeV onwards. Chlorine experiments went from about 1 MeV onwards. And the experiments of water challenge block started from 5 MeV. You can only get a spectrum of neutrinos for the super Cand SNOPs, only for the neutrinos which are more energetic than 5 MeV. So different experiments will talk about different ranges of neutrino. And this is what we saw in various experiments. This was the chlorine experiment. So chlorine experiment was the one which had this design threshold about 0.8 MeV, and it detected only UV. So it basically was sensitive to rest of bit 5. So this somehow measured the flux of electron neutrinos. The water experiments like supercarbonate, it looked at scattering of neutrinos with electrons. And we saw that actually what they measured was not simply the flux of electron neutrinos, but also about 1/6 the flux of mu and tau. So this actually is pi e. Plus 5 tau by 6. Then we had gallium experiments, which again measure only phi e, because they looked at reactions with the nuclei inside matter. So this was sensitive again only to phi. Then there was experiment with heavy water, D2O. One part of D2O was where you looked at this charge current events only. And that was sensitive only to UV. UV can no charge. So this is again only phi. However, other part was the experiment where you looked at total current events, in which you measured all the neutrinos together. So with all Neutrino, SNO, this actually measured phi E plus phi mu tau. Phi mu. So all these experiments are firstly at different energies, and they look at different combinations of phi E, phi mu. So we have to be able to explain all these things. The colors here correspond to fluxes coming from different reactions. So red stands for PP reactions, yellow stands for boron, and green stands for beryllium, and so on. Let's not go into details of that. This is another data. So this was only fluxes, only total flux. In addition to that, we also know the energy spectrum. So energy spectrum was given to us as super content, and that showed us that in the whole region, 5 MeV to 15 MeV, the probability of survival is almost equal to 0.45. So it actually measured, again, if you do it, measured phi E plus phi mu tau evaporescence. It has told us that this quantity is almost constant. With some variation, we will try to see what is the other. And then there is one last piece of data which I haven't shown you earlier, which is the data decimeter. So what do you do? Do something very simple. Divide your day into 10 equal parts. So 5 parts during day, 5 parts during night, and you determine what is the average of this. So you subtract. So this is N1, N2, N3, N4, N5, D1, D2, D3, D4, D5, and then you look at the number of events in each of these separate, each of the numbers. Okay. So whatever I get today between 12 and 2, I add to tomorrow whatever I get between 12 and 2. So I just made 5 different bins of this kind. Wait, 10 different bins, 5 day and 5 day. And then I plot it. So if you see here, you see that one may think that there is some kind of daylight asymmetry, very small extent, of the order of 1 sigma. So this is during day, during night. One tends to see that there is perhaps a slight excess during night. Okay. Even here, you see that this is day, this is night. So it looks like there is some excess during night. However, it's very small. The excess, if you look at this scale, this is maybe 0.45 and this is 0.47. 2% of change. So there seems to be some, but very small, asymmetry between day and night. So, but extremely small, almost negligible. So all this we want to now explain by using whatever we studied till now. So what did we study? We saw that the value of probability of survival basically looks like this. PF cosine squared theta 1 minus PF sin squared theta plus this interference. Okay. On top of that, we know that if gamma resonance is much greater than 1, we get expression that looks like this. If it's much smaller than 1, we get something that looks like this. Essentially, our parameters are delta and square and theta. So after doing all these things, finally we will fit to 2 parameters, delta and square and theta, just like we did for atmospheric gas. So now, another thing, of course, was daylight asymmetry, which we saw just some time ago. Okay. So, if theta is nearly 45 degrees, usually you are loaded in daylight asymmetry. If it's much smaller than that, you get some asymmetry. Okay, but again, that's just too long. But you can measure this part. So now that we know this, we go to the data and we do a fit to the data using two parameters, delta and square and theta. As expected, we will get some kind of contour plot in delta and square and theta, just like we got factors very quickly. So this contour plot is slightly complicated. That's because the solar neutrinos are slightly complicated. So you can see four different rate regions. Okay, 1, 2, 3, and 4. In these four regions, very different things happen. So it's not that you multiply something by 2 and you get some other thing. Okay, so we'll see what this is. Actually speaking, this allowed parameter space is very old. So this is 2001. But if I just tell you what the solution is now, it will be very boring. Because then it's just a global fit and meta solution. So therefore I want to explain to you the physics of all these four solutions, and that will give you more understanding of how neutrinos function. So these four regions are four allowed regions if you look only at flux. This is called as vacuum region or rack. This is called as low region or low mass square region. This is called as large mixing angle. LA stands for large mixing angle. And this stands for small mixing angle. So you can see this is tangent square theta. Okay. So this is almost at tan square theta equal to 1, which is 45. So therefore this is large. If you look here, this is tangent square theta of 10 power minus 3. So which is tan theta of 10 power minus 2 times something. So about 10 power minus 2, something like that, or 20. So now let's look at features of all these four positions and see what physics is in. Because at some point of time, all four of these give reasonably good solutions. It's only with the current data that we can rule out some.
Superconductor excluded by finite things.
So I'll come to that. That we are going to talk about. So right now just look at this four and then we'll talk about each of them individually. So let's first start with this solution, or vacuum solution. So what happens in vacuum solution? Delta and square is much smaller than 10 power minus 9 electron volts. 10 power minus 10. Here is about 10 power minus 10. This small region is 10 power minus 9. Much below it. Less than. Okay. So therefore, the resonance is in outer parts of the sun. Because delta times, so what do you need? For resonance, you need delta times cos 2 theta equal to Vc by 2. Since delta is very, very small, resonance happens when Vc is very, very small. In the outer parts of the sun, density varies very quickly. Inside it's very smooth, outside it's like a sphere, right? So near the surface of the sphere, so even if you have a uniformly charged sphere, at the surface the density changes very fast. So therefore, the resonance is very non-ideal. If you remember gamma had delta n square over 2e. Remember explain for gamma. Here delta n square is very small, 10 power minus 10. So gamma is very small. Therefore, this resonance is very non-adiabatic. And for non-adiabatic resonances, PF is simply cosine square. This is all. These two limits are very important. If PF is cosine square theta, then we can write down the whole expression. So remember we had this whole expression. Now we will substitute PF by cosine square theta. So this becomes cosine to the power 4 theta, sine to the power 4 theta, and plus 2 sine square theta, cos square theta, something. So let me show you what that something. So PE is cos to the power 4 theta plus sin to the power 4 theta plus 2 sin square cosine square times cosine of this. This is integral 2 delta dt, which is our oscillation term, and this is chi1 minus chi2. So now we see that apart from this chi1 minus chi2 part, this is almost like vacuum oscillations. So although the neutrinos pass through the sun, although they pass through an angle of resonance, the final expression for PE was almost like there was no matter. Just turns out that. Except for this phase which we do not know. Another thing is, see this 2 delta dt is of the order of 10 because the delta square is 10 power minus 10. Distance between Earth and the Sun is like 10 to the power 11 meters. You have 10 power 13 centimeters. Maybe I should do an item. L between Earth and Sun is nearly 10 power 11. 500 seconds of light. 500 light seconds. Okay, so if you want to look at how much this phase is like 10, maybe even smaller, because you divide by energy. No? If you want to look at 5 MeV, the phase is like 2. So this quantity is like 2. Therefore, if you measure the quantity to like 10%, you measure this phase to about 0.2. So you can measure reasonably accurately. So this phase information is available for us. Yeah, good. So there is some uncertainty in this phase, which will correspond to the radius of the sun times so delta x square L by 2e, where L is radius of the sun. Okay. The radius of the sun is much smaller than, so we saw that than Earth-Sun distance. So we saw that even more Earth-Sun distance, the change of phase is only about 2 to 10. So therefore, over the radius of the sun, the change in phase is very, very small. So that uncertainty due to not knowing where the production point is very small. Okay. So therefore, you don't have to think. Therefore, this is the particular case where you know the phase information. So if you have vacuum oscillations, then U1 and U2 will come coherently. And you will therefore see oscillations. So this is the only case out of the 4 scenarios that we talk about in which we would be able to see oscillations. The function of distance. So as a result, this gives me the following predictions. Firstly, it tells me that the flux is reduced because PE is not equal to 1. Okay. Also, my angle is 45 degrees, so this quantity is of the order of half. So I have color coding. Green means the data is satisfied. Orange means it's sort of shady, not very clear because data is not sufficient. And red means you do it. So here the green part is that it predicts reduced flux. It predicts seasonal variation. So it predicts that when you are away from the sun, you will see different angle of E. Okay, because distance L changes, and this involves this integral over L, okay, or T. So this predicts seasonal variation in E. Seasonal variation is the data is not conclusive because it's not difficult to figure out. Firstly, there is a variation because of the distance change from the sun. On top of that, you want to find small deviations because this E changes slightly. So therefore, although we have some data on seasonal variation, it's not very conclusive. However, once you look at energy dependence of PE, this should have energy dependence because this is oscillating. No? This is energy independent. This term is energy independent, but this term is energy dependent, delta n square by 2e. So if you look at 5 MeV and if you look at 10 MeV, this phase changes by factor of 2. And we can measure this to some 10%. So if there is a factor of 2 difference, we should be able to measure this. However, if you remember the data of spectral dependence, there didn't seem to be any change in energy. Energy dependence was almost non-existent. So if this term was present, then we will observe that there would be some sharp energy dependence, which meant as delta n square by 2. Turns out that this spectrum actually fits very well to a flat spectrum, and therefore the spectrum has no energy dependence. That rules out this solution. So therefore, although the vacuum solution seemed okay as far as flux was concerned, it failed on account of the energy dependence. So now we have thrown it out. We never considered it. Let's go to the next solution, which was the small mixing angle solution. MSW is the MSW resonance, and it's called usually SMA MSW because here MSW effect plays a large role. The vacuum solution, it played no role. So let's look at this solution again in our earlier. So this solution is here. Angle is very, very small, like 0.1 degrees. So theta is 0.41, 0.20, still small. So delta n square was like 10 power minus 6 to 10 power minus 5 electron volt square, and theta was 0.20. Now delta n square is 10 power minus 6, which meant that resonance was in the core of the sun, almost inside. Therefore, we have to now worry about our gammas and such factors, gamma resonance, diametricity. So before we go ahead, let me show you one feature of this. So remember, we had our PF. PF was nearly e to the power minus pi by 2 gamma. Gamma was delta n square by 2e times something. So sin square theta by cos 2 theta times 1 by c. What I want to emphasize is this actually looks like some constant over energy. So PF therefore normally looks like e to the power minus some constant over energy. Now we try to plot this. Because this has some very nice features. Okay, let's see what this will look like. So this is the energy axis. What happens at large energies? At large energies, P will be close to 1. So at large energies, it's almost horizontal. What happens at low energies? It becomes equal to 0. Actually, if you try to plot this, you will see that the plot looks something like this. So this is, let me plot of this is small and large, we plot in a long space. Actually goes like this. So there is some energy interval E in which it goes from 0 to 1. If you are in this region, which is non-adiabatic. If you are in non-adiabatic regime, PF is flat, no energy dependence. If you are in adiabatic regime, PF is flat, no energy dependence. But if you are in this transition regime, PF depends on energy. So that's again one of the rule of thumb to keep in mind. If If you are not completely adiabatic or not completely non-adiabatic, then PF depends on energy. That's exactly what happens for this SMA solution. In SMA solution, gamma is of the order of 1. Okay, so not very small, not very large. So your PF actually depends on energy. You can change between 0.2 to 0.8. So somewhere in the middle, not 0, not 1. Another thing that happens is the following. See now delta M square is 10 power minus 6. Okay. What is the distance between Earth and the Sun? 10 power 11 meters. So if you take 1 MeV neutrino, the total phase generated is like 10 power minus 6 times 10 power 11, 10 power 5. So total phase generated is 10 to the power 5. It's 1 lakh. So even if I measure it to the accuracy of 1%, but error in the phase is 1000. It basically means I don't know the phase. Right? Since the phase is 10 power 5, even if I measure it to 1% accuracy, the error in phase is 10 power 3. It basically means I don't know the phase. Therefore, there will not be any oscillating phase. I will only get the first two terms. So my probability of survival will simply be PF times cosine square theta plus 1 minus PF times sin square theta. Okay, so the third term will decide by completely get some oscillating. However, only thing to note is that this PF will depend on energy. So the PF will have a different value at 5 MeV and at 10 MeV. Okay, so we should see some energy dependence. Not only the energy dependence is monotonic, because see gamma is monotonic function, right? So the PF is monotonic function of E. So we shouldn't go up and down. We should monotonically go up. So survival probability should look something like this. This is what we expect for the SMA solution. So what will you predict then? You will predict that the flux is reduced, which is fine, okay, because this is not equal to 1. Second thing we will predict is that daylight asymmetry is very substantial. See, that's because remember this rule of thumb again. If the angle is large, 30 degrees, 40 degrees, 50 degrees, it doesn't change much in the one. The angle is very small, it changes quite a lot. Now here, mixing angle is 0.1 degrees. So inside the Earth it will change a lot. Okay. So therefore, there will be very substantial daylight asymmetry. And as we saw, the data of daylight asymmetry gave us that the asymmetry is very small. Okay. Less than some 2% or so. And that is this solution. Okay. So although this gives you reduced flux, it predicts substantial daylight asymmetry, which is not observed. It also predicts energy dependence of PE. So this is energy dependent. Okay. However, we saw in the spectrum that the value of observed flux was almost constant. Okay. So therefore, this is also known. Only when better and better data came, did this solution start getting ruled out. Okay. About 10 years ago, people were still wondering as to what the exact solution is. Let's go to the third solution. This is the LOW solution, the low solution. Okay. It is this solution, the small. Okay. So this has delta n square of 10 power minus 7, and angle is almost 45 degrees. Yes. Again, the resonance is in the core of the sun. Gamma is of the order of 1, not very large, not very small. Therefore, PF is between 0.2 and 0.8. So therefore, there is energy dependence on PF. Again, if you want to calculate the phase, it is about 10 to the power 4. phase 10 power 4 means that even if you measure it to 1% accuracy, error is 100, so you can't measure it. So it's equivalent count. Therefore, again, probability of survival expression looks very similar to the SNA solution. So again, predictions were flux was reduced, which is okay. Here angle was about 45 degrees. Therefore, we predict no linear asymmetry, which was okay. What we saw was very, very small. This was okay. However, this shows you that EF has energy dependence. So this EE should have energy dependence. The dependence was not observed. This ruled out this. So it's mainly the energy dependence of PE that ruled out this solution. So in that sense, the spectrum that we saw super content played an extremely important role in lots of solutions. Now let's go to the solution called as large mixing angle solution or LAM. So what was this solution? So let me again go to this solution lies here, this big red block. So it has a time square of the order of 10 power minus 4 also, and theta is not exactly 45 but maybe 35. So now angle was large, delta square was large. Okay. If you remember gamma went up with delta m square, gamma went up with sin square 2 theta. Okay. This was a solution where delta m square was also the largest, theta is also the largest. Okay. Therefore, gamma is very large. So gamma is very large, so PF is almost equal to 0. Okay, this e power minus gamma. Again, if you look at the value of phase, it was like 10 power 6, again very large. See, large delta m square means large phase, okay, because phase is proportional to delta m square. So phase was very large. Even if you measure it 1%, you are off by error in phase is of the order of 1000, or maybe 10,000. Okay, so forget about any kind of coherence. But survival probability now is very, very simple because PF is 0. Only term that survives is this 1 minus PF times sin square. So probability of survival is simply equal to sin square. So what does this mean?
One thing, you just repeat one thing. From what logic you are getting that delta m dt, I mean interference term? I mean order of that term you are getting in each of the things.
So delta m dt, so we can group it. So you want to calculate delta m dt, integral to delta m dt between sun and earth. Right? So what is this? This is integral delta m square L by 2e. Okay. And can you remember this is whatever 2.5 delta m square in EV square, L in meters, and E in MEV. Yes. L in kilometers, E is in GeV. Okay. So we are now at this. So delta m square is very. So delta m square is 10 power minus 5. So this is 2.5. L is 10 power 11 meters, and E is 1. And this is already 10 to the power 6. Just 10%. A very quick estimation. Very often for this physics kind of arguments, you don't need to calculate exact numbers, or just some order of numbers. So P is now a very simple expression. So what are the predictions? Flux is reduced, which we observed. Okay. No desired asymmetry, fine, because it is only sin square theta. And angle is near 45 degrees, large angle. So therefore, theta m doesn't change much. So no desired asymmetry. This was that. And very important, no energy dependence in PE, it is just equal to sin square theta. And we saw that the spectrum that is transferred to Kamiokande is consistent with flat spectrum. So it satisfies all these three things. Therefore, this was a solution that survived after all the data that we got in the last period also. So it's an ironic thing that after all these things, the solution that actually happened to be close to the truth happened to be extremely simple. The survival probability is simply sin square theta, nothing else.
No oscillations. No oscillations.
Of course, oscillations. You see, yeah, no observed oscillations.
No oscillation to the problem.
No oscillation problem. Just sin square theta. So this means wherever you measure it, you can go near the sun's surface and measure value of PE. It will be equal to sin square theta. See, there is no dependence on the distance from us. People are detecting oscillation. So then I come all the way here to work. This is sin square theta. So the probability of survival does not depend on where you are. The atmospheric case is dependent, right? It depends on how much neutrons are traveled. Some have traveled 10 kilometers, some have traveled 10,000 kilometers. And the probability dependent on that. Here nothing, just sin square theta. Therefore, you can also imagine that if you want to fit it to two parameters, delta square and sin square theta, you will not know much about delta square. You only know that delta square should be large enough that the resonance is adiabatic. Where did we use delta square in all these calculations? We needed delta square to satisfy this condition. So as long as delta square is high enough that resonance is adiabatic inside the sun, this expression is okay. But if you just measure this quantity, you will not know anything about delta square. So in fact, therefore, you see that this blob is very vertical. So we know the value of theta very well, but not delta square. This is, here you will see that the difference is of the factor of almost 10. So as long as you are above this, you are reasonably. So these are the features of the solution that we do. So this took lots of different experiments and inputs and spectrum and so on. But everything was depending on the sun. So you are happy with this? So now comes the final step, which is now that we know that we expect that we understand the sun well, we should be able to reproduce the same solution by looking at material state experiment on the we produce neutrinos and we detect neutrinos. Before that, let's look at this plot again, okay, because it's question or not, right? So these red points are the ones that we saw now, which are allowed by the flux. The green part is that which is allowed by the day-night spectrum and boron. So we look at day-night spectrum, right? What did day-night spectrum tell us? It told us that there should not be day-night asymmetry, so angle should be large. So you see that this bluish part tells us that angle should be large. Okay, so that actually ruled out some of these earlier solutions. Then the blue line says SK excluded by day-night and spectrum. For example, look at spectrum. We saw that we ruled out this vacuum part by using energy spectrum. Okay, because this vacuum part gave energy dependence, we saw no energy dependence. Similarly, this area was excluded by using energy spectrum. Sometime later, after this plot was made, even this part got ruled out because of energy spectrum. When this plot was made, this low solution was allowed, but now is that we know this.
Flow is excluded due to day-night symmetry.
Energy spectrum. No, this is allowed. So this painted part is allowed by day-night asymmetry. So it was allowed by, because low had 45 degrees, so no day-night asymmetry. So after this plot was made, low got ruled out because of energy dependence. So we needed some more detailed data to be able to do that.
I mean, all the three characteristics you are saying, I mean, one is true, the other is not valid. They can be read from this thing because But if it is in allowed range of day-night spectrum, then it is violated by only energy, day-night asymmetry and energy spectrum.
So this top part happens to be the area which is allowed by everything. It's allowed by flux, this red part. It's allowed by day-night asymmetry, that's very small. It's also allowed by spectrum because it falls outside this. So finally you only get this small. And this small part, we will come to what this small part is. But this is a small part and finally this. This is the area solution. So the oops. Now comes the question. So now we'll come to the experiment on Earth. Make some neutrinos and we detect it somewhere. You put it at reasonable distance so that, see, now you don't want to have obligations of this battery effect. So you don't want resonances. Because as we saw, solving for resonance, MSW resonance inside the sun is very difficult task. Okay. Now you want a very simple oscillation experiment. Produce neutrinos here, detect them here, and they go as sine squared delta m squared by 2e. Now you want an experiment as simple as that. It does not involve battery. If you do the experiment, and if you find that the values that it predicts for delta m square and theta exactly overlap with this LMA solution, then you are confident that what you have done is correct. Okay. So, a very ingenious experiment was designed. Again, this was in Japan. The most difficult part of an experiment is producing neutrinos. Okay. Detecting is in some sense easy. You make a detector and then you take neutrinos from the what the Japanese did is they figured out that the site of the Kamioka experiment was such that it was surrounded by many nuclear reactors. All nuclear reactors give UV bars. We know nuclear reactors, so we know what the energy spectrum is. So firstly, reactor gives lots of neutrinos because they have very large energy output. Secondly, they were all within some 200 kilometers or so. And thirdly, it so happened that this predecessor of Super Kamioka, just Kamioka experiment, happened to be in the location which was sort of central. See, Japan has many nuclear reactors. So, this is the site of Kamioka. And all these rays that you see show you where reactors are. So reactors are here, 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 and so on. And from all of them, neutrinos will travel to this experiment. The experiment is called as CAMLAT. CAM for Kamioka, liquid, ND for neutrino detector, LA, I forgot. Okay. So, therefore, you will look at flux from all these 10 different reactors. Of course, length is very different. So, for each of them, probability will be different. Okay. But you take probability for each, multiply by the flux of each which you know, and you take average, you sum them up. That's not a big deal. So, concept theoretically, it's a very simple thing. Okay. All you want to do is you want to look at summation of EEE, so neutrino, from detector, so let's call them I, times flux of UV bar from I. So you measure this, and by measuring this, you can fit for two parameters, right? So this PE will basically depend on delta m square, theta, and a distance from the detector. So Ni. All these, so Ni is known, only two parameters are delta and square and J. So once it was designed, then the results came within a matter of maybe a couple of years. Very fast experiment. So reactors were already on. All you have to do was to put this detector inside this tunnel. This was some old Kamioka tunnel. This is a network of tunnels. So this from this picture set. This was a reactor made of synthetic. Some hydrocarbon. Now for reactor neutrinos, the expected spectrum without oscillations was this top curve, so this grayish curve. There was some background. Observed was this. So data is of course this. The crosses that are shown on data points. The best fit for oscillations, first background, was this red curve. Oh, sorry, green. So this green curve gives you the best fit. So now this best fit corresponds to some delta and square and some theta. Okay. So now we combine that with the earlier LMA experiment. Let's see what that is. So this region is the LMA region. Okay. Remember that it calculated the theta very well, but wasn't sensitive to delta and square. Now here, Kamnath experiment was sensitive to delta and square very well, but not so much to theta. So theta is very uncertain, okay, but delta and square is very certain. So these are the parameters of Kamnath. So finally you combine Kamnath and solar and get your best fit solution. Okay. So you can expect that basically the best fit will lie somewhere here. So good thing is that both of them overlap. Better thing is that overlap region was kind of orthogonal to each other. So we actually got a very small region. So I think I have that region. I don't have that region. So you can imagine that the region that we have is actually a very small region. So now solution is the following. Delta and square lies in a very small region, like 7 to 8 times 10 power minus, should have been 5 electron volt square. So a very small region, within 10% or so. Sin square theta lies around between 0.25 and 0.37. See, note that in the case of atmospheric neutrinos, we measure sin square 2 theta because the probability of survival involves sin square 2 theta. In the solar case, we always give sin square theta. That's because the survival probability involves sin square theta, just equal to sin square. Another feature is that the propagation is almost adiabatic inside the sun. E is always equal to sin square theta. No energy dependence, no design asymmetry. It turns out to be finally a very simple solution for solar model. And that can now explain almost everything else. You say, satisfying all this was actually possible with many solutions, but the most difficult part of the spectrum was satisfying the spectrum of superconductor, flat spectrum. And the solution of LMA actually satisfied. So finally we have this solution, and since 2003 or so, I think 2002 was the one was the year when we zoomed in on the LMA solution. Kamnath gave his results in maybe around 2005 or so. From that point of time, we are reasonably certain that at least to the first order, when you talk about 2 neutrino mixing, the solar solution is so we'll stop here. Next week onwards. So now we have seen 2 solutions: atmospheric solution, which was mixing between u and u tau with 2 neutrino mixing. We saw a solar solution, which is between u e and something. He never cared about what it was. He said you knew arbitrarily, but no, maybe something different. So what we'll do starting next week is to try fitting all these things into 3-minute movie. So I expect that before we start it next week, just go through lecture notes and so on.